Okay. The exams are all graded. I'll have them for you on Wednesday. I have to do some assessment stuff, and I won't. If I put the grades on Canvas, I'm going to mute them before, so you won't see the grade before you get your exam back. I do that because there was an incident a few years ago. We'll call it the Jill incident, where I left a one off of her score. So instead of like having 150, she had like 50. And apparently it caused quite a mental trauma overnight, lots of sobbing. So then when I handed it out, she came and she's like, "You gave me 52 instead of 152. And I said, "Okay." And then I realized it would created the trauma, so I don't release the grades until I give you the exam back. That'll be on Wednesday. Okay, what I'd like to do is to finish up before we jump into Chapter 5, which is actually the first traditional organic chapter. I wanted to go back and talk a little bit about where we left off with the acidities, because I don't know how to get these questions online where you can answer them. And even then, we should go over them because there's some similar problems to finish up Chapter 4. So, just to go back and remember where we were, I guess last Monday. When we have an acid, and this is true of a base as well, that we'll see, but whenever you have an acid in equilibrium with the H plus and A minus, and A minus is called that acid's what? It's the conjugate base. So how do we push this equilibrium to the right? What do we do? Make the product more stable. With any equilibrium, if you make the product more stable or make the reactant more unstable, you can push the equilibrium to the right. And then vice versa if you want it to go to the left. So there's many ways that we can make the A minus more stable. And I think I skipped over the question about oxygen base or oxygen acids. But if we had, for instance, if we have an alcohol, if we had water, if we had a carboxylic acid, and then we can also get a little bit more sophisticated by having what's called a sulfonic acid. In terms of acidity, the one that has the most stable conjugate base is going to be the strongest acid. So for instance, I'm going to think about this CO minus, which is called an alkoxide. Or I'm going to think about the hydroxide. Or I'm going to think about the carboxylate. And then I'm also going to think about this, which is called a sulfonate. So our rule here is we want the most stable conjugate base is going to provide the most acidic acid. So what I'd like you to do for a minute is think about how you would rank these in terms of stability. And I'm talking here about the bases because then we'll work the reverse to get to the acids. So which one of those bases, which one of those conjugate bases is the most stable, the next most stable, etc. Bless you. So I'll give you, I'll give you 2 minutes, and you can discuss if you'd like. And if you don't know, go back to that basic principle. And if you're like, how do I apply that? Think about, well, what could make that molecule more stable? I'll give you a hint, it starts with R. Do we all have a ranking? Bless you. Okay. Then let's see, I've got 4 choices. So I just sent out a multiple choice question. Tell me which of A, B, C, and D, which one is the, sorry, not most basic, most stable. So of A, B, C, and D, which one is the most stable? Okay. Anybody else? Anybody else left to answer? Okay, make sure you answer one today. 20 people say D. Okay, why? If you were one of the 20 people that said D.
I thought that both the oxygens have a 0 formal charge, oxygen has a negative charge.
Okay. Everybody want to build on that?
So all oxygen spread out the negative charge.
By doing what? How's it going to spread out the negative charge? You're right. You're exactly right. The oxygens are going to end up, they're all going to take a negative charge, but how? Can you see that happening? We'll come back to the inductive effect. The inductive effect would come from the group that's actually attached to sulfur. But instead of with an inductive effect, what else is also possible? My hint was it started with R. Resonance. So I can write I can write two more resonance structures for that sulfonate group, right? Well, I shouldn't say right because apparently it's not that obvious right now, but it will be. So let's say I take this pair of electrons, move it here, and then move the pair of electrons out to that oxygen. Okay, so there's one of the resonance structures, and then I could bring this pair of electrons down here, move that pair of electrons out to form the third resonance structure. So there are my three resonance structures. And then what would the hybrid of this be? The hybrid of this would be to take and write the single bonds of the oxygens and average bonds and charges. So each one of the oxygens is going to have what average charge?
Partial negative.
A delta minus. You could say, well, how about minus a third? I don't care about the exact number. I care about the fact that it's between 0 and minus 1. So each one of those oxygens has a delta minus. And then what about partial bonds? Each one of the sulfur oxygen would have what kind of bond? A partial double bond. So each one of those bonds has a partial double bond, and each one of the oxygens has a partial negative charge. So you're right. We're spreading out the negative charge. And anytime we spread that out, which is also called delocalization, that's going to stabilize the structure. So we're stabilizing it by drawing resonance structures. Okay. Can I do that for any more of these structures? Can I use resonance to stabilize any more of these conjugate bases? Which one? You were nodding your head. So the carboxylate, I can do the same thing, right? For the carboxylate, I could make it COO, partial double bond, partial negative, partial negative. So for the carboxylate, I can do the same thing, just one less time. So the sulfonate is going to be more stable than a carbonate because it has one more resonance structure. That's going to stabilize the sulfonate, and it's going to do what to its conjugate acid? it's going to make it stronger. So a sulfonic acid is stronger. Well, sulfonic acid is the strongest of the group, followed by a carboxylic acid. And you know that because it's a sulfonic acid and it's a carbonic acid. So therefore, what are they? Acids. So that's kind of our resonance, what we can call resonance effect. I can push and pull electron density by being able to write resonance structures. And that actually turns out to be much more powerful than electronegativity pushing and pulling electron density. Okay. Which is what we saw last week with the carboxylic acids, which I'll go back to, the acetic acids, like attach a chlorine or a fluorine to it. Then you're using an inductive effect. You're pulling the electron density out. Okay. So I have two ways to make a negatively charged species more stable. Pull the electron density out through electronegativity or spread it out through resonance, with resonance being more powerful. Does that make sense? Now, what about the alkoxide and hydroxide? What should we do with those? Well, for the alkoxide, let's say that I have an alkyl group attached to the O-. Is that alkyl group going to make the alkoxide more or less stable? So in other words, if this is a primary alkoxide, and I had a tertiary alkoxide, which one of those two would be more stable? And remember what I said a minute or two ago. Two ways to make the oxygen minus more stable. Do what or do what? Pull electron density out through some sort of electron negativity effect, or delocalize it, spread it out. So can I spread it out here? There's no other resonance structures for this. So I'm going to have to pull electron density out of that oxygen. So which one of these do you think is more stable? A or B? And let's just go ahead and vote on that. Let's see, what am I doing? Oh, I'm asking another question. Multiple choice. Okay. Your choice is A and B, and there is no C because it's got to be A or B. Which one of these is more stable? Okay? Let's see, what are our answers? Our answers are mostly B's. That B is more stable. That's interesting. Why is B more stable? And what was C? I didn't think there was a C. C must mean, I don't know. Why was B more stable? I'm confused. And trust me, I'm not the only one. So, what have we done with alkyl groups in terms of delta plus and delta minus charges? If I come back over here, well, here, I'll just make an alkyl group. Here's an alkyl group. Where should my charges go? Delta plus should go where? Carbon or hydrogen? So the hydrogens get the delta plus. Who gets the delta minus? Well, the carbon, because that's all that's left. So that carbon now has a delta minus charge. So I'm going to come over here and I'm going to say, oh, that carbon has a delta minus, this one has a delta plus, this has a delta plus, and this one has a delta plus. What's that carbon with the delta minus going to do? Does it want it? Does the carbon want the delta minus charge? It would like to get back to neutral. So what's it going to do? Push. Where? It's going to push that electron density where? To the carbon it's attached to? Ultimately, it's going to push the electron density to this carbon, but that carbon's going to do what? It's not really going to do anything with it. So, okay, I'm done asking questions. I'm going to make definitive statements. That carbon will push electron density to that carbon that's attached to the O minus. That is not helpful. Because how should the electron flow go? Or how should the charge flow go? It should go in the opposite direction, right? Whatever's attached here should be sucking the electron density out of this carbon and then sucking the electron density out of that oxygen so that everybody gets closer to zero. By putting an alkyl group there, I'm doing what to this? I'm actually destabilizing it. Because the electrons are being pushed when they want to be pulled. Does that make sense? No? What doesn't make sense about it? Because this carbon has delta minus charge. And so what it wants to do is it wants to get rid of that, and so it's going to push it to this carbon. But that carbon doesn't want any more negative charge, right? Because it's already got a negative charge on this side. So what we'd like to do is we'd like to have the electron density kind of do this. Let's just say for the sake of argument that I'm saying to you, okay, let's say I make a fluorinated ethyl alcohol. This has the right flow of electrons. When the alcohol gets deprotonated, I have a negative charge. What are all the fluorines doing? They're all pulling electron density out of the carbons. And by pulling electron density out of the carbon, what happens to the oxygen's negative charge? It's going to flow into that. So some of the O- is going to end up in the fluorines. But I'm basically pulling the electron density away from the O-. And so this one would be the most stable of all. If I put a halogen onto an alcohol, that's going to make that alkoxide, the conjugate base, the most stable. And we saw that a week ago, although it was a week ago, when we substituted a halogen onto, let's say, an acetic acid, then the halogen was pulling electron density away, and it was pulling electron density away from the CO-. So this is what we call an inductive effect. This is when you're pulling and pushing electron density by using electronegativity differences. And so to make the O- species more stable, you've got to suck the electron density away from the negative charge and spread it out. And here we're kind of spreading it out into the halogen through electronegativity effects. What is not stabilizing is to push electron density into a negative charge. That's not going to stabilize it. And so having a fluorine here would stabilize it, just having a CH2 doesn't. And of course, the more alkyl groups you attach to the carbon with the O-, what's going to happen? It becomes less stable because now I'm pushing even more electron density in. Right? This carbon's delta minus charge was great for what? Carbocations. Right? It was really good for carbocations because it helped stabilize the C+. But in this case, that's not what I want. I want something that's going to pull the electron density out of the O-. So what was the correct answer here of A and B? What's most stable? A. Because A only has one alkyl group, whereas B has 3. Right. So the correct answer was, where's my correct answer? I'm not using that in grading you because this week's going to be, I need to go through all the participation stuff in the first 3 chapters and get all that stuff on to Canvas as well to sort of counteract the exam so you know where you're at. But it helps me. So if you were one of the 2 people who said A, congratulations, if that's the reasoning you used. If you guessed, congratulations, you're a good guesser. Does that make sense? I mean, we're getting into a lot of topics here, and what I'm trying to emphasize is the fundamental rules. Because if you keep track of the fundamental rules, I can ask you any question and you can work through it. And the fundamental rules being, starting with, how do you push the equilibrium to the right? By making A minus more stable. How do you do that? Well, you could do it by resonance structures, or you can do it by electronegativity effects. Any questions? So then we'll go here. We'll go to my oxygen-containing species here, and I'll push this out in a minute. And you can answer, and you can match it, most to least. I'm sorry, match the pKa. Oh no, I didn't say which one was more stable. I said pKa. So now what are we going to have to think about? Which one of these acids is going to have the lowest pKa? The one that is the lower the pKa, the blank the acid. Stronger. So the strongest acid is going to have the lowest pKa. The strongest acid is going to have what kind of conjugate base? The strongest acid is going to have the weakest conjugate base, but let's replace weak with stable. The strongest acid is going to have the what conjugate base? The most or the least stable? The most stable. Okay. So if we need to map that out. Meaning, strongest acid, most stable conjugate base. Also weakest conjugate base. Okay? So, in order to match these up, you have to say, okay, let's look at their conjugate bases. Which conjugate base is the most stable? And work your way back up. This is the same problem I gave you, sort of, except now it's got a benzene ring in there. And so you got to figure out what to do with the benzene ring. So the question is to rank. You've got 5p. I don't know why there's a dot in front of the 2, but I don't think it's significant. Oh, I know why there's a dot there. Because it's supposed to be a -2. So C is -2. It isn't. Why not? Let's try it again. Let me end it. And let me... Wait, do I have to... Wait, sorry, I have to close this question first. Then maybe it'll show up. Now is it showing up? No? All right. The hell with the pKa's. I'll give you 2 minutes. You can rank them. Strongest to weakest. Acid. Are we ready? All right, I'm going to go back. I'm going to end this. And I'm going to go back to my on the fly mode. And what do we need? We need 5 choices, right? Okay. All right, which one is the most acidic? A, B, C, D, or E? Okay. Now we're split between B and E, which I actually kind of expected. Somebody give me an argument for E. Why E's the most stable? Somebody that voted for E. And this is the last day that, because come hell or high water on Wednesday, I'm going to have your names in here so that I can just randomly start calling on people. So today's the last day you can kind of hide down. All right, somebody have for B then.
E is more stable because it has 3 different resonance structures.
Okay. How many resonance structures does B have? Give me a number. How many people have I humiliated when they've given an incorrect answer this year? Not previous years. Previous years the trend may be greater than 0, but this year. I don't think I've done that to anybody yet. And if you feel that way, that's certainly not intended. So 10 people voted for B. Did you think that it has resonance structures? If you voted for B, how many? How many do you think it has? You want me? I'll create a safe space where any answer is correct. Give me a number.
3.
3. It's a good number. That's correct. So that goes back to, so if I had an O minus here and I had a double bond there and a double bond there, I could bring this pair of electrons there and move it out here. And I can do that 3 times. Katie?
Oh,
Now you're going to give me an answer for E. Good. Okay.
Okay.
So what's your answer for E?
So I said E more than the inductive effect because there's more oxygen to keep the partial negative effect of the oxygen is important with oxygen. And rather than like the E where there's the carbons that already have the partial negative, because there's that sort of hydrogen. That's what I said. That.
Do we like that? Does that answer sound? So in B, I'm spreading the charge out over 3 more carbons. And in E, I'm spreading it out over 2 more oxygens. Does that sound reasonable? That the oxygens are going to want the negative charge more than the carbons? I mean, have we said that before? So I like that. That got me out of a little bit of a jam. Because that's the way that we would want to think about this. Actually, E is the most stable, then most acidic. E, then D, and then, we got a D and a C. So E more than D and E, C and D. We'll deal with C and D in a moment. And then B. Because those 3, I'm spreading the negative charges out over oxygens as opposed to carbons. So that's a really good answer. Another part of that answer that you don't know yet, but you will now, is that when you have a benzene ring, whenever you have a double bond, 2 double bonds separated by a single bond, this is what's called a conjugated system. And whenever you have a conjugated system alternating double, single, double bonds, it's more stable than having 2 double bonds that are not separated by a single bond. So when you put double bonds in conjugation, they become more stable. The ultimate conjugated system is to put alternating double bonds in a 6-membered ring, which is why this is benzene. And this is the ultimate conjugated stable system. When we learn about reactions of double bonds, benzene doesn't do any of those. Benzene is super stable. It's flat. We have to work really hard to get it to react. It's what's called aromatic, which means that it's super stable in addition to having a particular odor. But for our purposes, the idea of spreading the charge over carbons versus oxygens will work. Part of the reason is because if I break up the benzene ring, if I break up that conjugation, then none of those resonance structures are particularly stable. But we'll come back to that. I like the other one because I didn't know how I was going to get out of that other than explaining this way. So that's a good answer. Where am I at? Okay, so if the negative charge is on oxygen, better than having a negative charge on a carbon. How about C and D? There's a methyl group here, and there's a hydrogen there. So if I'm thinking about my O minuses, which one do you think is going to be more stable as its conjugate base? The H with the O minus or the CH3 with the O minus?
I said the H, the CH3, when the H is pushed into the C and then that C push into the main C.
Exactly. So we have that inductive effect of an alkyl group. It'd be better to have formic acid with an H is going to be a little bit stronger than acetic acid with the CH3 because the alkyl group is not pulling the electron density out, it's pushing it in. So it would go E, C, D, and then B, and then finally A. So E, C, D, B, A. And decreasing strength of acid. Does that kind of make sense? I think the questions, because I still have a few more questions, I have 3 more questions. I have alcohols pKa matching, phenols pKa matching, and amines pKb matching. Let's just take a look at the alcohols here for a minute. Oh, we've seen this, haven't we? So we're matching the alcohols pKa's primary, secondary, tertiary. But now I'm looking at acid strength. So what did we say? When you put an alkyl group onto an alkoxide, what happens to the alkoxide? Does the alkyl group stabilize or destabilize the alkoxide? Destabilizes it. So in terms of acidity then, you have a less stable conjugate base, which means you have what kind of acid? Weaker. So which one of these is the weakest acid? Primary, secondary, or tertiary? Tertiary. Phenols. Oh, this is fun. So when we have phenols, you'd say, well, they all have the same resonance structures, which is true. They all have 3 additional resonance structures when you make an O-. But now what I'm doing is now I'm beginning to use inductive effects on the ring. So what does a CH3 group do? Does it push electron density into the ring, or does it suck electron density out of the ring? It pushes it. Is that good? No, that's not good for making a stronger acid. How about a nitro group, though? What do you think a nitro group does? It pulls the electron density out because it has a positive charge. But also, if I pull electron density, I can move the oxygen double bond, the O-, so it actually has both an inductive effect of pulling through that charge, but it also can do it by resonance. Nitro groups love to suck electron density out of rings. And so is that a good thing or a bad thing for acid strength? That's going to be good. It's going to make a stronger acid. So combine this with last week's, and what I'm showing you is all the different ways that we can strengthen acids or we can weaken acids. But it's all done through the conjugate base. How do I get that negative charge either spread out, pulled out, or push negative charge in, which is bad for making a stronger acid? Does that kind of make sense? So hopefully then that would let you finish off the chapter 4 problems, which I'll put a deadline on and Friday. So I won't look at the chapter 4 problems and total up the points until Friday. I can't, what I'm finding is I can't put a deadline on these chapters because when I do, they disappear. And then I make them reappear and they disappear again. And I don't know how to stop that from happening. So I'm just going to leave these open, and then I'll send an email and say, this is when I'm going to start looking. You can gamble and gamble that I'm not going to look at them then, and that's probably a pretty good gamble at the beginning. So what we're going to look at is Chapter 5, and there's actually some videos that I'll put in the book that you could watch on 5. I'll send out exactly what we'll do for Friday.